Good morning to one and all. Today I would like to deliver my paper in MFO algorithm based profit maximization. MFO algorithm based profit maximization of distribution companies by optimal placement and sizing of DGs under deregulated environment. On 4th International Conference on Electrical and Electronics Engineering. Now my paper ID is 4321. Track 1 is related to the power generation distribution systems. And myself, SKB Pradeep Kumar CH, working as Assistant Professor in Ramchandra College of Engineering. And my co-authors are Balamurugan G, Buchiraju Sir Y, and Pasupuleti Babu Rao. Now coming to the abstract, for over a decade, distributed generations have successfully convinced the researchers that they are the economic and environment friendly solution that can be integrated with the centralized generations. The optimal planning of distributed generation requires the appropriate location and sizing and their corresponding control with various power network types to obtain the best of the technical, economical, commercial, and regularity objectives. Most of these objectives are conflicting in nature and require multi-objective solutions. Among many studies proposed to solve the DG placement problem, only a few papers have addressed this issue from DG owner's perspective, none of which has taken the important role of transmission costs allocated to the DGs into account. Therefore, in this paper solves the multi-objective optimization, voltage stability problem under deregulated environment. The prime concern of the problem is to maximize the profit of distribution companies called as a discourse by optimal sitting and sizing the distributed generation units in radial distribution systems called as RDS. A simple and parameterless algorithm of mouth flame optimization is used by solving this problem and to achieve the best solutions. In addition, voltage stability enhancement and real and reactive power loss reduction have also been carried out by using a single DC unit, its optimal place of installation, operating, and maintenance costs also calculated. Now, the proposed method has been included in the IEEE 33 and 69 bus distribution test system. The performance of the approach is assessed via simulation, and the findings are compared to other existing methods like fuzzy computing as well as differential evaluation algorithm. The comparison validates that the suggested method increases discourse profits in a radial distributed system. It is realized that the proposed MFO is one of the best meta-heuristic approaches to solve complex multi-objective nonlinear optimization problems under regulated and deregulated environment. Now coming to the problem formulation, it plays a major role for getting the more profits in discourse. The prime objective of this study is to maximize the profit of DC owners and minimize the various costs of discourse. Profit of DC owners is mathematically represented as follows. Maximum of F is equal to MPF, where NPV or MPF or NPF factor, which represents net present value, can be represented as NPV, and IF, inflation rate, IR, interest rate. Now, MPF is equal to sum of benefits minus sum of expenses. The present cost value of C, that means the cost of DG generation, is represented in the equation. Now, the benefit of evaluation is this cost actually includes the sum of energy loss reduction cost, which is taken as American dollars 0.05 per kilowatt hour, and the cost of DG generating power at dollars 300 per kilowatt hour. Now the next parameter is cost of energy loss reduction. Initially, the load flow solution for the test system is solved without DC to read real power loss, and again the process is represented with the presence of DC. The difference in losses represents the net loss reduction in the equation 4. That is NLR. Net loss reduction is equal to P loss minus loss due to DC. The obtained loss reduction with the DC is converted into cost value in equation 5. That is, cost of net loss reduction is equal to net loss reduction into cost of energy saving per kilowatt hour multiplied by 8,760 hours. Now, the present cost value of CNLR is calculated in NPR of C of NLR is equal to CNLR sigma of T is equal to 1 to N gamma of T, where T is equal to 1, 2, up to so on N, where CNLR is the cost of net loss reduction. Now, the next parameter is cost of DC power generation. Now, the type of DC power considered for this study is a solar PV system. The data for this cost is taken from reference 6 and is calculated using equation 7. Now, cost of DC generation is equal to DC size multiplied by DC generator cost per kilowatt per year. The present cost value of DC generation is estimated as NPV of C DC generation is equal to C DC generation into sigma of T is equal to 1 to N gamma T. We know that T is equal to 1, 2, 3 up to so on N, and cost of DC generation is equal to cost of DC power generation. Next parameter is expenses cost. This cost includes the sum of DC investment cost and cumulative of the operation and maintenance cost of DC over the period. Now, the next parameter is operation and maintenance cost. Now, the cost includes the operation and maintenance of DC connected to the grid and is calculated by using the equation. Now, the operation maintenance cost details of DC placement were taken from cost of DC operation maintenance is equal to DC size multiplied by DC operation maintenance per kilowatt in a period. The present cost value of DC operating and maintenance is calculated as NPV of cost of DC of operation and maintenance should be equal to cost of operation and maintenance multiplied by sigma of I is equal to 1 to N gamma T. And the next parameter is investment cost. The investment cost of optimally placed solar PV type DC is calculated using equation 11. Now, the cost of DC investment is equal to DC size multiplied by DC investment cost per kilowatt. Now, the economic validation of the above discussed objective function depends on the optimal location and rating of DC. Now, the implementation plays a crucial role for solving this problem and improving the profit of discourse. Now, initialize the parameters of mouth flame optimization algorithm such as population size, elite size, and a maximum number of iteration number. Randomly generate the populations, that is P of MFO, using a heuristic algorithm subjected to the system constraints. Evaluate the objective functions of each population and determine the DC owner's profit and discourse cost. Now, we have to set the iteration count. The iteration count initially should be equal to the 1. Calculate the fitness function and evaluate the fitness function and calculate the mouth by placing DC. Already we are explaining in the previous slide, we have to place a proper place for the DC at their respective buses. Evaluate the objective functions of each mouth and determine the profit of DC owners and various costs of discourse. Update the positions of flame and save the best fitness values in an array corresponding. Update the record of flames and the flames are arranged based on their fitness values. Commutate the present position of mouse. Check all the constraints are satisfied. If yes, move to the next step, or else go to the step 6. Check if the number of iteration process is equal to the maximum number of iteration. Otherwise, go to the step 5. Display the global best solution of various costs of discourse of profit of DC owners. If you satisfy, then stop the program. Now, after applying the mouth flame optimization for placing the best DC, then the results we have to obtain. Here the table 1 represents voltage profile for base case placement of DC in IEEE 33 bus system. Already we are just explaining that we have to do the best DC in two test systems, that is IEEE 33 and IEEE 69 system. Now these are the results. Now the corresponding simulation results for getting the outputs. The figure 1 shows the voltage profile for base case replacement of DC in IEEE 33 bus system. Now in the graph I am representing, highlighting base case voltage and lighting the MFO voltage. Now by using MFO algorithm, we have to improve the base case voltage also. Now in figure 2, which represents the base case placement for DC in IEEE 33 bus test system. Now for this voltage source index for a base case placement of DC in IEEE 33 bus system. These are the results. And the simulation results of IEEE 33 bus system after 1 year of planning period. Already various cost of energy loss reduction. By using fuzzy with a DE algorithm, we can get 39.89. Now that cost can be reduced by applying MFO algorithm, that is 36.43. Cost of DC power generation per year is 341.16 and MFO proposed is 407.77. And operation and maintenance cost should be fuzzy with DE is 18.19, MFO is 21.7. And investment cost is 2302.86 and 27.56. And the simulation results of IEEE 33 bus system after planning period. Now, obviously, if you are observing this tabular form, by applying mouth flame optimization algorithm, we have to reduce the cost and improve the benefit, and we have to increase the total profit of discourse. Just we have to compare by using fuzzy and DE algorithm, the profit should be $15.35 million per year. But in the case of MFO algorithm, we have to improve the profit as $17.78 million per year. Now these are the comparison graphs and convergence curve of IEEE 33 bus system. Like that, we have to go for IEEE 69 test system also. These are the results, and these are the corresponding simulation results for IEEE voltage profile index as well as voltage stability index also. Now we have to check the comparisons of the IEEE 69 system. Now the total profit of discourse should be $26.57 million per year. And the expenses also 5.61, and benefit of the discourse is $32.18 million per year. And the investment cost also very, very low. And operational and maintenance cost also reduced. And the cost of DC power generation should be limited. And the cost of energy loss reductions also improved by applying mouth flame optimization algorithm. And this is the convergence curve of IEEE 69 bus test system. Now, coming to the summary of this paper is, in this work, it solves the voltage stability problem under deregulated environmental using mouth flame optimization technique. The proposed methodology effectively maximizes the profit of DC owners and minimize the various costs of discourse, and it also improves the voltage profile and reduces the network losses in IEEE 33 bus and 69 bus node test systems. Moreover, the comparison study made with fuzzy and differential evaluation algorithm to evaluate the performance of proposed MFO algorithm. Thank you.